Hello kids, welcome to Mammoth Online, where all concepts become unimaginably easy. So today's topic is mathematical reasoning. So to understand mathematical reasoning, first we have to understand what is reasoning. So the idea behind reasoning is very simple. The Google definition of reasoning is basically logically and systematically trying to arrive at a decision or some kind of conclusion or explanation. So that is reasoning definition. Makes complete sense. For example, let's say you got a call from somebody you know. Okay, it could be your friend, it could be your parents, or if you have a girlfriend, then girlfriend. But let's say you couldn't pick their call. Now what will happen? Because you couldn't pick their call, you'll call them back, right? So when you call them back, you will logically and systematically try to create some kind of explanation. Now that is called reasoning. Okay, so now we do this every day. Now, when we do this kind of thing for maths, we call it mathematical reasoning. Now, how do we do this for maths? Let's understand with some example. You would have seen that the number root 2 is irrational, which means it is a surd. Now, how do we know that root 2 is irrational? There is a beautiful proof there. For example, the opposite of irrational is rational. And rational numbers obey certain properties. If you have a rational number like 1 by 3, or you will have something like 3 by 10. So what you see is rational numbers generally have p by q form, where p and q are integers and q is not equal to 0. So now, to prove that root 2 is irrational, we do something very clever. So what we do is, we'll assume, let's say, root 2 is rational. Understand, root 2 is not rational, but we will assume that root 2 is rational. If root 2 is rational, then obviously root 2 should obey all the p by q conditions. So that is what mathematicians try to do. They made a sentence like, if root 2 is rational, then root 2 will obey p by q conditions. Now here there are two sentences. Okay, one is root 2 is rational. The other sentence is root 2 can be expressed as p by q form. Now in a world where we don't know whether root 2 is rational or irrational, now in that world, root 2 is rational is an assumption statement. So if root 2 is rational, that is an assumption, then root 2 can be expressed as p by q. That is a conclusion. Now this entire statement becomes a third statement, let's say. So that kind of statement is called if and then statement, which we will learn in depth in later classes. So if root 2 is rational, then it can be expressed in p by q form. So basically they understand that that statement entirety must be true if root 2 was rational. Now they see that after applying the condition of p by q, it fails. So the idea that root 2 can be expressed as p by q is false. It's a very simple proof actually. So now we are in a scenario where if conclusion is false, what about our assumption that root 2 is rational? Is it false? Is it true? So now starts the game. We have to guess whether root 2 is rational or irrational because the conclusion was false. Now let's see how we do that.
Now let's say root 2 is rational. So we are in a world where we don't know if root 2 is rational or irrational. So we are assuming that root 2 is rational. And if root 2 is rational, then our conclusion is that root 2 will be in the form of p by q, where q is not 0 and pq belongs to integers. So this is our statement 1, assumption statement, and this is our statement 2, which is a conclusion statement. Statements are A and B. Now, if we have a statement like, if a number h is rational, then h equal to p by q, where q is not 0 and pq belongs to integer. If we have such a statement, that statement is true, because that is the definition of a rational number. So if a number h is rational, then h can be expressed as p by q in simple terms, and q is not 0 and pq belongs to integers. So therefore, if we can write that if root 2 is rational, then root 2 can be written as p by q, where q is not 0 and pq belong to integers. Now this statement is a new statement. Let's say this statement is C. This is called compound statement. If root 2 is rational, then root 2 can be written as p by q, where q is not 0 and pq belongs to integer. This entire statement is a third statement, let's say C statement. Now we know that this is false, but the entire statement C is true. The compound statement is true because any rational number can be written as p by q. But the second statement, our conclusion, root 2 equal to p by q, the statement B is false. So what about root 2 equal to rational? Is it false or true? That we have to figure out. So to understand this, let's take a very simple scenario. Now imagine I have two statements. Statement A is it's raining. So you are standing outside your house and it's raining. Now statement B is ground is wet. Okay, these are two independent simple statements. Now let's say it's raining outside, therefore this statement is true, and the ground is wet, let's say this statement is also true. Now understand, if the compound statement, that is, if it is raining, the ground is wet, this is the compound statement, if it is raining and the ground is wet, if that entire statement is true or false depends on A and B statements. Let's understand that. Now if it is raining, let's say there is a statement which is, first statement, that it is raining and the ground is wet. Both are true, both are happening. So if I create a statement that is, if it is raining, the ground is wet, that will be this statement. Obviously it's going to be true. If it is raining, then the ground is wet, that's a true statement. So this is true, this is true, this is also true. Now let's see the other scenario. The other scenario is, it's not raining and the ground is not wet. It's not raining will be the false statement, because if it's raining is true, it's not raining is false statement. So let's say I have a statement like, if it is not raining, then the ground is not wet. That statement is also true as a compound form. The compound statement of if it is not raining, then it is not wet should be true. Okay, so that's very simple. Now let's see one more scenario. Now that is, if it is raining, which is true, then the ground is not wet. Now that is not possible scenario, because if it is raining and the ground is not wet, it's not possible, ground will be wet. So therefore the statement is false. That is, our assumption is true, but conclusion is false. So therefore the entire compound statement is false. Now let's talk about the last scenario, which is little tricky. Many people confuse here. So let's understand this. If it is not raining, that is the false statement, because raining is true. So if it is not raining, then the ground is wet. This is also true, because the ground could be wet using some other means. Somebody is watering the ground, or there was a flood, or there was some kind of water leakage, whatever, right? So even if our assumption is false, if conclusion is true, then our statement, if then statement is true. Okay, so this is the simple scenario when we have such situations. Now let's apply this situation for root 2. Now we understand that from this, if a statement is true, because we found out that if a number is rational, it can be expressed in p by q form, and that entire statement is true. So if the compound statement is true, these are the three scenarios possible. Now in this, we figured out that root 2 cannot be expressed as p by q, as shown here. So our conclusion is actually false. So what happens when we have conclusion false? So we are seeing that if the conclusion is false, that is, there is only one scenario like this where conclusion is false, then our assumption must be false. That's the only possibility. Now let's apply this for root 2. That is, we have two statements, that is, if root 2 is rational. So this is statement 1 A, and root 2 can be expressed as p by q, where q is not 0 and pq are integers. This is statement B. This entire statement is C. Now we know that entire statement C is true. For any rational number, it can be expressed as p by q. So this statement entirely is true. Now if that is true, we know these are the three possibilities, and among this we know we have proven that the second statement B is actually false. The conclusion happens to be false. So if conclusion is false, that is happening only here where we have getting false. Now if that is false, then definitely our assumption must be false. Therefore, root 2 is rational. This statement A is actually false. If this is false, what is a true statement? True statement is root 2 is irrational. This is the only possible scenario.
So we see that the only possibility of that happening is when root 2 is irrational. So that is how we can prove that something very fundamental in maths, like a number is irrational, using just statements. So that was very wonderful. Now let's increase our level and let's understand how this is used in much more fundamental concepts in maths. So guys, in maths there are relations, okay? Just like relations we have in our real life, maths has relations. So what is relation? Basically there'll be a set A and there'll be set B. Now between these two sets you can have connections. Now these connections are relations. In technical term, relation is basically subset of all the ordered pairs. So let's understand that.
Now basically when we have two sets, let's say A and B, and we want to find a relationship between them or some kind of connection between them, we have this kind of ordered pair. That is, x1 is mapping to y1, x1 is mapping to y2, x1 is mapping to y3. So all this sort of mapping we get from here. And that particular set is called ordered pair. Now this is our ordered pair set. It has 9 elements because there are 3 elements here and 3 elements here. So totally we will have 9 elements. Now when we want to find a relationship between A and B, basically this ordered pair we have to choose. We can choose one or more. So such choosing is called subsets. So basically relationship between two set A and B is basically a subset. So if we have all the subsets, we will get all the relation possible. So there are 9 elements. So totally there are 2 to the power 9 relations possible because those many subsets are possible. Among all these relations, one relation is very, very important. That is, you can have a subset which has null elements, which means no elements. Imagine you are a person and there is one other person across the street. There is a possibility that you are not siblings in that context. So therefore, there is no relationship between you both. So a null relation is pretty much possible. Null relation does not have any ordered pair. So this is our null relation. So it's a special type of relation. Now, if you have a null relation, then we have some interesting questions to ask.
Now in relations, we group them into different categories. And few of those categories are very simple. One is called reflexive relations, then we have transitive relation, and then we have symmetric relation. So let's understand if null relation is symmetric, transitive, or is it reflexive.
Every relation can be divided into 3 categories. We can say transitive, we can say symmetric, we can say reflexive. There are many groupings also, but for now let's understand these 3. Now my question is, if we have a relation R1 which is phi or null relation, will this be transitive? Will this be symmetric? Will this be reflexive? I want to figure this out because in exam they will ask if a relationship is transitive, or they will ask how many transitive relations are possible, how many symmetric relations are possible. So we must know if a null relation is transitive or symmetric or reflexive. So let's figure out. So let's start with transitive. Now transitive relation is basically a mapping between two identical sets. So here we have A and we have another set A. Both are identical and they have elements ABC, small abc. Now a transitive relation basically says if we have like A comma B and B comma C, then A comma C must exist. As you can see here, if A is related to B and B is related to C, we must have A related to C. It's like family relation. If one person is related to one other guy in the family and that another guy is related to some other third person in the family, then the first guy and the third guy are also family members. It's as simple as that. So A to C we should also have. If such situation exists, then we call it transitive relation. So my question is null relation a transitive relation? Let's understand that. So the statement is, if A comma B exist and B comma C exist, then A comma C must exist. Then a null relation will be transitive. So here we have two statements. If A comma B and B comma C exist, then A comma C must exist. So we have two statements. Let's say this is statement 1 and this is our statement 2. So this is again if then statement which we saw just before. So we know A, B, B, C. Statement 1 is definitely false because a null relation does not have any elements. So this is false, and also A, C must exist is also false because a null does not have any elements. So clearly statement 1 is false and statement 2 is also false. So when both are false, what happens to the resultant statement? This entire statement which we have constructed, if then statement, what happens to their value of truth? Now we have seen in the previous tables, that is, if both statements are false, that is, both statements are false, then the resultant statement will always be true, as we can see here. So therefore, if statement 1 is false, statement 2 is false, then it is true. And this is why in Google they say that a null relation is transitive vocatiously. They say it is vocatiously true because of this reason that statement 1 is false, statement 2 is false, so therefore the entire statement must be true according to our understanding of logic. So that is why they easily say that it is vocatiously true statement throughout. So therefore we can understand that a null relation is transitive. Now let's talk about symmetric relation. So what does symmetric relation say? It simply says that if you have A, B, then its symmetric element, that is B, A must also exist. Then it is actually symmetric relation. So is null a symmetric relation? Let's understand. Now the statement is very simple. If A, B exists, then B, A must exist for symmetric relation. Now they are saying if A, B exists, then, so we have two statements here. So that is A, B exists, then B, A must exist. So there are two statements. Let's say this is statement 1 and this is statement 2. Now we understand that statement 1 is false because for a null relation, statement 1 is false, and similarly statement 2 is also false because in a null relation there are no elements. So when that happens, we have seen that according to this table, we see that our assumption is false and our conclusion is false, then the resultant compound statement's value is true. That means definitely for null, the statement is true. That is, null is actually equal to symmetric relation. Now let's understand reflexive relation. Now reflexive relation is very interesting. See, it doesn't have if and then statements. It has very simple understanding that any relation is reflexive if you have A, B, B and C, C. Then you can have other elements, doesn't matter. So basically you need all these elements mapped to itself. Basically the element ordered pair should have a reflection of itself in ordered pair. So that should happen for every element. So a relation is reflexive if you have all the elements must map to itself. So A, B, B, C, C must exist. For any relation, A, B, B, C, C, these ordered pair must exist for it to be reflexive. So it must exist. But you see that in null there are no elements. So must exist statement itself is false. So therefore a null relation is not reflexive. So in conclusion, we are understanding that a null relation is actually transitive, a null relation is symmetric, but a null relation is not reflexive. So as you can see, just using statements, we have proven some of the most fundamental things in mathematics.
Basically, using just simple English statements, we can prove some of the most fundamental properties in maths. And that is why mathematical reasoning is one of the most powerful tools we have in maths. And this is also very important when you talk about preparations of mains. One question definitely comes from this topic. In the next video, we'll talk about how to apply these concepts even better. Bye-bye.